This week is back to looking at dose-response models to estimate risk. To recap, a dose-response model describes the relationship between how much of something gets to a specific part of your body and the magnitude of the effect that its presence causes. Today, we'll look at two of the simplest models around. These are still used by risk assessment experts and offer tremendous insight into the risks presented by different substances and how they can be managed. To start with, we have the threshold model. Imagine you breathe in a lungful of carbon particles from the back end of your car. Thanks to millions of years of evolution, your lungs are pretty good at handling inhaled particles, so your body gets rid of the particles, repairs any damage that they cause, and you remain hale and hearty. That is, until the amount of stuff you inhale overcomes your lungs' ability to handle it. Once you pass this threshold, the more particles you inhale, the more damage is caused, and the greater the risk to your health is. This type of response, and it isn't limited to particles and lungs, can be modeled with a threshold dose-response model. At low doses, the body can handle the stuff, so you're exposed and there is negligible risk. But above a threshold dose, the body's defenses begin to struggle. An increasing dose leads to increasing risk. According to the threshold model, if exposure is kept well below a certain level, risk is minimal. But what if you're exposed to something that causes irreparable damage? It used to be thought that this was the case with substances that cause cancer. Here's how the thinking goes. Imagine a chemical gets into the nucleus of a cell and messes with your DNA. Now, imagine that messed up DNA is replicated every time the cell divides. So rather than your body getting rid of the problem, it makes it worse. And at some point, that messed up DNA could potentially lead to cancer. Now you have a situation where a higher dose means greater risk, but there is always some risk associated with dose, no matter how small that dose is. In other words, there is no threshold. This no-threshold dose-response model is still used to estimate the risk associated with exposure to cancer-causing agents. Of course, both of these models are wrong. Just like all models, they have their limitations, but they are useful. We now know that DNA damage and repair are more complex than previously thought, and so the no-threshold model is oversimplistic. We also know that people respond to non-carcinogens in complex ways, and so the threshold model is also oversimplistic. But each model still provides risk assessment experts with valuable insight into the harm that exposure to a substance might cause. And they provide a powerful starting point for thinking about the relationship between dose and response and what this means for understanding and managing risk.